So we're going to be going over the worksheet 2 answers. And with each of these problems, the first thing you should do is draw a free body diagram after you read the problem. So after reading the problem, it'll kind of identify what forces you should expect to see, and then you should draw in those forces on a free body diagram. So we're going to start with just a traditional free body diagram. There's no angles here, so it's straight up. What force acts in the downward direction vertically? Gravity. All right, that should always be where you start. That should be your comfort zone. So we've got the force of gravity going downward, and then what's making the helicopter accelerate upward? What kind of force would we call that? We'd call that a lift force. Now, conceptually, if it's accelerating upward, are they equal? Are gravity and lift equal? No. Which one's greater? Lift will have to be greater because there is an upward acceleration signifying a net force in the direction of that acceleration, which in this case would be upward. So I'm just going to give myself a little note here that acceleration is upward. So this is the qualitative portion. You should have been able to handle this much for sure. Now comes the slightly more difficult part of, well, what do I do next? Well, qualitatively, I have to set up a free body diagram and then a sums of forces. That should be the process you go through every time. So let's go ahead and set up a sum of forces in the direction of acceleration, which is going to be the vertical direction. So I'll call this the sum of forces in the y direction. In the positive direction, I've got my lift force. And then in my negative direction, I've got gravity. So then we see that this is the only forces acting on the object. If that's the case, then this must equal MA. There is an A here. In this case, there is an acceleration, so there's a value to the right. We cannot say that they are equal because there's an acceleration. One of them must be greater. So what we can calculate, because what it wants you to know is determine the lift force of the helicopter. So that is what we are looking for. That means that gravity must be available. All right, just as a reminder, force of gravity will always equal mg. So the mass here is 4,600 kilograms. And our little g is always 10 meters per second squared. So your force of gravity is going to be the mass times 10. That gives us 46,000 newtons downward. So that means that gravity pulls downward on this helicopter with 46,000 newtons of force. And yet the force of lift is still greater than that, enough to cause an acceleration of 2 meters per second squared upward. So we know that the acceleration is 2 meters per second squared upward, and we know that the helicopter has a mass of 4,600 kilograms. So there must have been a net force proportional to those two values. So net force here must be equal to mass times acceleration. That's what this statement on the right says. I've just expanded the statement of what net force actually is. I want to figure out what this value right here is. So that's going to be equal to 4,600 times 2. That's going to be the mass times the acceleration. Well, we are going to get the net force for this entire helicopter is going to be 9,200 newtons. So that means that after the lift force battles against gravity, it wins with a margin of 9,200 newtons. That means that it must be greater than gravity by that value. So we plug these values in and we find that the force of lift, well, if we see this, the force of lift is equal to, how do I get rid of gravity here? Well, if I'm adding a negative, technically subtracting, so I would just add the gravity over to the other side. So the force of lift is equal to the force of gravity plus that net force. All right, now we have values for both of these. We have just solved that net force is 9,200 and that the force of gravity is 46,000. So we plug those values in. Force of gravity here's 46,000 plus 9,200. And this is equal to 55,200 newtons. This must be the force of lift that the helicopter exerts on the air in order to have an acceleration of 2 meters per second squared. So when you have acceleration, this is coming from the net force. The leftover forces after the opposite forces of gravity and lift cancel out, and then there's extra lift force to cause that acceleration. So notice that the lift force is greater exactly than or it's greater than gravity by exactly the amount of net force. That's how net force works. So that is the answer to number 1. All right, so you couldn't say that these were congruent. And then the rest of it is math. So just reminding you, you did a qualitative free body diagram. You then did a qualitative sum of forces. You knew you needed to calculate MA and FG in order to calculate for the lift force. So that's what we did over here on the left. Then we added them together based on this equation here, where I just rearranged my net force equation. And that's how I solved for the lift force. So this one was relatively straightforward, or mainly straight upward. And then we're going to look at number 2, which gets a little bit hairier. It's not quite as simple of a problem because you're having to think about an object being accelerated upward by a pulling force. So one of the things I will tell you is that whenever you have a problem like this, where something is attached to a rope being held and lifted or dropped, so in this case, it's just being lifted, then we're going to use the idea that the force is equal to mg plus ma or mg minus ma. So we're going to go ahead and draw a free body diagram. So what forces are acting downward? Gravity, as always. So we've got the force of gravity of the groceries. So the container is the bag, and the bag exerts what? A normal force upward, right? So it's going to have a normal force upward. Now, before it gets accelerated, it's just being held. Are they congruent? Yes, they are, because if the bag doesn't rip immediately, then normal force must be equal to gravitational force because they're in equilibrium. You're just holding groceries. So whenever you take groceries out in the bag, as long as you're not lifting it up or down, normal force within the bag, the resisting force, is equal to the amount of weight of the groceries inside of that bag. These two would be congruent. Now you have added an additional force. There's an extra force being added to the system, and that would be the applied force. You can call it whatever you want. I'm going to call it the applied force because you're pulling it. You could call it the force of pull, the force of tension, but it is applied nonetheless. So this kind of is a blanket terminology. There'll be an applied force upward. And how do I know that there's an applied force upward? It gives me an acceleration upward. That tells me that there's an extra force upward. And it causes the whole bag to accelerate upward at 5 meters per second squared. So that means that net force is equal to mass times acceleration. It's the same way we set that last problem up. So we've done a qualitative free body diagram. Let's do a qualitative sum of forces equation. So we find that the that the sum of forces in the y direction are equal to what's in my positive direction. In this case, I'm going to put this in parentheses, normal force. Then we also have force applied. Then we'll subtract that force of gravity. All righty. So what we're going to see here is that I want to see whether or not the bag rips. Well, the problem reads that it can only withstand 250 newtons. All right, so right now we have no numbers, but we know that the maximum value that that bag can hold is 250 newtons. So the first thing we're going to need to know is, well, does it rip before you accelerate, right? Does gravity already equal that amount? So we got to figure out what the force of gravity is. As always, force of gravity is equal to mg. This being the case, it's going to be the mass of 20 kilograms times 10 meters per second squared giving us a value of 200 newtons. So the force of gravity is 200 newtons downward, which means that that normal force it exerts is 200 newtons upward. And really what this is saying is that the bag can only add 250 newtons of resistance in order to keep the bag from ripping. If it goes over 250 newtons of resistance, it will rip. So we then have FA, which gives us an extra force. Well, how much is that extra force? Well, that extra force, again, normal force was balanced against gravity before you accelerate. That extra force here will be equal to that F applied, going to be equal to mass times acceleration. Well, we already know that the acceleration is 5 meters per second squared and that the mass is 20. So we say 20 kilograms times 5 meters per second squared. Maybe you noticed the relationship between the last problem, which was 10. So it'll be half of that previous. This is 100 newtons of force. So you've added 100 newtons of force into the system. So what you're going to do here is you have to determine, is this going to rip? Yes or no? Well, as you pull and accelerate, you add 100 newtons. And I want you to think about this conceptually, because though the force applied is upward, your inertia for the groceries suggests that it wants to stay where it was, correct? So it's going to resist that extra force. So the inertial mass wants to stay exactly where it was. And then you accelerate upward suddenly. So the equation that we use is that the force that we're actually checking for is equal to mg plus ma. Now, the reason we do this is because inertia is going to make the groceries resist moving. So there's going to be this moment where the bag's moving, but the groceries don't want to. And if that applied force is greater than 50, because gravity is already pulling down with 200 newtons. If that applied force is greater than 50, then the bag rips, because inertia states that those objects don't want to move and they're going to resist it. And if they resist hard enough, the bag can't withstand that resistance and you will see it rip. So what was mg? Mg was 200. And then ma we calculated to be 100. So what does this come out to be? Comes out to be 300 newtons. 300 newtons is greater than 250 newtons, and the bag rips. So that's the answer there. Because of inertia. Inertia is coming from Newton's first law, and it's the resistance to motion of all matter. All matter resists motion. So, do you have any questions about that one? All righty. Now we move on to number 3. And number 3 is a very similar problem. It deals with inertia. So, though we see, let's see, we're going to see 3 scenarios, and technically we're going to do math for 2. So standing on the scale at rest, this is just regular force of gravity. The weight is 840 newtons. So Fg equals mg, and Fg equals 840. G always equals 10, so mass must equal 84 kilograms. I went ahead and did that because anytime you get gravity, that means calculations are available. You get mass, calculate gravity. If you get gravity, calculate mass. As the elevator rises, well, think, you were not moving upward, and then you started moving upward. Matter resists changes in motion. So your inertia states you want to still be down there on the bottom of the first floor. And so you're going to resist that change in motion. And it's going to be an upward acceleration, and your body resists that upward acceleration. So the scale temporarily reads at 1050 because your body's still trying to be where it was. All right, so then we find that this force here is 1050. Then it returns to normal. So there's this extra force. Well, how do we find out that extra force? Well, let's do a sum of forces equation after having done a free body diagram. So gravity down, of course. There's a normal force upward. In a stationary position, these two are equal. Then you add an applied force. Now this applied force, again, applied force is a blanket term. This is technically a tensional force. There's a tensional force in the rope above that elevator that pulls it upward. So then we've got this right here. Well, let's look. Well, if the acceleration is positive, just like in the last problem, this is the same problem. You've just been given the value here. So really what this means is that that force that the scale reads is the sum of these two right here. And you are trying to figure out how much extra force was added. Well, we want to know what that extra force was. What's that applied force? We set up a free body diagram to do a sum of forces in the y direction. Normal force plus Fa minus mg. That's the force of gravity. This equals ma. All right, well, I know that this term right here, normal force plus the acceleration or the applied force, that's what the scale reads. So this is 1050. mg, I already calculated that m was 84, and we were given that 840 is the force of gravity. This equals ma. So we then can state that the difference between these two is 210 newtons. This is equal to 84 times the acceleration due to that motion. Have we followed so far how I got here? I set up a sum of forces. I plugged in the value that the scale reads, which is that upward force total. Then I subtracted gravity, and the difference between those two has to be net force. That's what causes the acceleration. And that's technically this value right there. 210 is the applied force because normal force equals gravity. And then you have an additional applied force. So we've got 210, and then you divide everything by 84. And you find that 210 divided by 84, you probably don't know this one off the top of your head, is equal to 2.5. Roughly, I mean, it rounds to 2.5. So this is equal to an acceleration of 2.5 meters per second squared. Then we look at the second scenario. The second scenario, you're at the top and you start going down. Well, let's look at that free body diagram. I'm going to set this up right here. All right, the first two forces are the same this time. All right, force of gravity goes down. Normal force goes up. When you're at rest at the top of the elevator, these two equal each other. All right. Now, we look at the fact that, well, you were not moving, and then suddenly you started to move downwards. So your velocity went from 0 to a negative value. That means you have a negative acceleration and thus are accelerating in the downward direction. That means the force is downward. So the applied force here is downward. So we do the exact same thing we did last time. We set up the sum of forces in the y direction. The only thing that changes is that it's normal force minus Fg plus Fa here. All right, and this equals ma. Well, this value here is 840. It was always 840. It was 840 in this first part of the problem, and we added the 210 to get 1050. All right, so we have that 840 minus, well, what's this value right here? 588. So what you're actually going to have here is that this is equal to let me erase that really quickly. So FG here is, of course, 840. And then plus, well, what value would give you 588 for this right here? All right. You got to look. What's the difference between 588 and 840? Make sure I've got the number right before I say it. It is 252. So that applied force has to be 252. All right. So 840 plus 252 gives you 252 greater than 840. And then when you subtract that from 840, you'll get 252 less than 840. Does that make sense? Which will give you 588. Do you see how that works? You give this value here, which would be 1092. 840 minus 1092 is equal to 588. All right. Yeah. So this equals MA. And we find that the acceleration here, is that right? Okay, I see what I did. Minus. That's the issue. So this plus needs to be a minus. I wrote it wrong and I was just following the math. Let me erase that really quickly. Okay, so here you're going to solve for FA instead of solving for MA so that you could then use FA to solve for MA. So let me go back and do this. Then you're going to state that it is this gives you the 252. You set that equal to mass times acceleration, where mass is 84. I still did not erase the thing I needed. And we find this to be 252 divided by 84 is equal to 3. So it comes out perfectly there as 3 meters per second squared. So I want to show you something that I mentioned in the last one, and it's this idea right here. mg plus ma, and in this case, we'll also have mg minus ma. So if I go through for this portion right here, mg was 840, ma was the mass times the acceleration. So we don't know what that is, but we do know what this force is. So you essentially say this, so it's the force of gravity, the regular force, and you want to solve for ma. So you're going to find the difference between the force reading on the scale and the force of gravity. So in the case here, you find that the force difference between the scale and gravity is this 210, and you set that equal to ma. The force reading on the second one is different by negative 252 because you'll say this if N minus that gravity is equal to ma. So then you get negative 3 meters per second squared. So setting this up is just good practice, but whenever you've got an object that's being held and accelerated upward or accelerated downward, the scale reading is equal to mg plus ma or mg minus ma. And then last, we've got to apply that in a really weird way. We've got it's kind of a combination of number 2 and number 3 put together. So when we look at that, it's got a maximum value. We have to determine whether or not or what acceleration will get us to this value. So we know that the tension can only hold 30,000 newtons. So the sign on the elevator states that 20 persons, which is 20 people, can fit on that elevator. Assuming that each person is 75 kilograms, if we just do a really quick math, then the mass of all people would be 20 times 75, which I think is 1,500, equals 1,500 kilograms. Then we've got the addition of the elevator. The elevator is an additional 500 kilograms, and the cable has to support all of them. You'd add 500 kilograms. You'd find that the total mass of the system is 2,000 kilograms. And this is how much mass. So then you could then say, well, what's my free body diagram? Let me not do it right there. I'll do it over here. And of course, we've got the force of gravity of that elevator and the people. Then we're going to have the force of tension upward supporting that. And they'll be equal to each other. Now, this statement that they're equal to each other means that the acceleration at which you add extra force, an applied force, an additional applied force would make tension go and have to resist that acceleration. So we state that this right here is the mass. Go back to black. Fg equals mg, where m is 20 or 2,000 and g is 10. So this is equal to 20,000 newtons. Just like last time, it's going to be this equation right here, mg plus ma equals Fn. So what we have is that the force of gravity, just traditionally, mg is 20,000 newtons. I know that the maximum amount of force that this elevator can support is 30,000 newtons. So if we subtract the difference between those two, how many newtons of extra spare room, wiggle room, does that elevator have? And it only has 10,000 newtons worth of extra room. This would be the maximum applied force on that elevator that it could withstand. So if this is the net applied force, how do I solve for acceleration? Set this equal to mass times acceleration. mg, so in this case, it is the total amount of force that it can withstand minus that force of gravity. That gives me how much wiggle room I have here. It can withstand up to an additional 10,000 newtons. Well,
so you just divide that with 75?
Not quite, because it's not just one person. It's going to be the total mass of the system, which is 20 people and the elevator itself. So that ends up coming out to be divided by 2,000.
Well, so the average rider, so don't you have to do 20 times 75, or is that 500?
That's 1,500, and then you add in the mass of that elevator, which gives you a total of 2,000.
I was confused how you got the 1,500. All right, now
1,500 was 75 times 20. Okay. So 10,000 divided by 2,000. Hopefully you know what 10 divided by 2 is, and all the zeros go away.
100.
We are not quite.
No,
not quite.
Wait, I'm like 1, 2, 3. Oh, it's 5.
There we go. So 5 meters per second squared is equal to our acceleration. It can only withstand 5 meters per second squared, and at that point, it would break the cable. Now, that same idea can be used for number 2. If you go look at number 2, it has a maximum of 250, so we'd say 250. And then it has a force of gravity of 200. So what this means is that it only has a wiggle room of 50 newtons. It can only withstand an additional 50 newtons of force. You set that equal to mass times acceleration, and here you determine the maximum amount of acceleration you could use on that bag without it ripping. Well, the mass was 20, so 50 divided by 20, well, 5 divided by 2, and then take the zeros away, the maximum acceleration that the bag could withstand was 2.5 meters per second squared. So you accelerated it twice as fast as it could handle. All right, so you could apply that same idea to another problem as long as you have that maximum value as one of the values stated. All right, so I'm going to go ahead and make sure, does anybody have any questions about how this works? All righty, so that sounds like a plan.